get started in just a minute. Again, if you keep cameras off, thank you. So we're going to be starting again. We finished the last chapter, so we're going to get started here in a minute. We're going to start on chapter 13, which should be gases. Okay, so we're going to pick up with chapter 13. So this is about gases. So obviously, we are talking about the state of matter, which involves gases, right? So when we do get to the gas state, we're at the state of matter where everybody has pretty much broken away from each other. They're flying around, as we'll talk about. As they're flying around, it hits the wall of the container, for example. They hit other gases and the walls of the container. And that's really what it sort of associates pressure with what we think about when we think about gases. And we're going to obviously talk about pressure. We'll also talk about a lot of sort of gas laws that are related. There will be a number of laws that you'll have to obviously memorize and remember in this chapter. It involves pressure and calculating pressure and temperature and volumes and those type of things. All right. So when we talk about gases, let's talk about sort of the idea of what substances exist as gases under normal sort of pressures and temperatures. So under normal pressures and temperatures, sort of room temperature, if you will, that usually is a pressure about 1 atm. Atm is an atmosphere. That's a unit of pressure. We don't get money out of it or anything like that. So atm is an atmosphere. 25 degrees Celsius is typically kind of normal pressure. It's usually, 25 degrees Celsius is the normal temperature. And that's usually the normal temperature that we see in things like tables where we do constants and that type of stuff. So under sort of normal conditions, that is essentially what we consider kind of normal everyday, like you're standing in a laboratory type conditions in most cases is 1 atmosphere and 25 degrees Celsius. Now, when we talk about ionic compounds, which again are our metals and our non-metals that come together, remember that they're held together by the transfer of electrons. So really no sharing of electrons there. What holds them together is that electrostatic attraction, that positive charge from the cation and that negative charge from the anion. That's what holds an ionic compound together. And ionic compounds are held together by these electrostatic attractions, which are very, very strong intramolecular forces, which means within the molecule. And usually under normal conditions of, say, 1 atmosphere and sort of room temperature, if you will, to overcome those forces, you would have to supply a tremendous amount of energy to do that. And that typically doesn't happen with ionic compounds. So for example, if you took something like sodium chloride, which obviously is, find my pen there, which is a little crazy today. Sodium chloride, which is an ionic compound, again, not sharing of electrons holding that together, but actually the cation and the anion coming together to hold that unit together. If you take something like sodium chloride, which is salt, and we did it, I think, in a couple of experiments towards the beginning of the semester, where you took your evaporating dish and you heated it and got rid of all the water, and you were left with sort of a residue in your evaporating dish. And what you're left with at the end there is still the sodium chloride, for example, solid. The best that you'll see happen with an ionic compound is it will start to melt rather than go into the gas phase, which is good for something like salt, right? Otherwise, when we put it on our fries, right, we would get like chlorine gas and stuff like that, which we probably would not want and stuff like that. So because these ionic compounds are held together by these really strong forces, um, under normal sort of conditions, sort of everyday conditions, we typically don't find ionic compounds in the gas phase. They don't usually go into the gas phase. They're usually a lot of times solids. Now, covalent compounds or molecular compounds are a little different than that. Uh, covalent or molecular compounds, again, are guys that are basically nonmetals together. So we're sharing of electrons here. So when we're sharing of electrons, there are certain things that how they naturally come is they naturally come as gases. So things like carbon monoxide, carbon dioxide, that's hydrogen chloride gas, NH3, which is ammonia, CH4, which is methane. It's an organic compound. The simplest one you could have is also like the gas that comes out when you light your Bunsen burner, so it's very flammable. But there's a lot of molecular compounds under normal conditions that do come as gases. But a vast majority of them, which are solids and liquids at room temperature, the difference between sort of a covalent compound and an ionic compound in terms of the gas phase is it is much easier to convert usually a covalent compound into a gas than it is, say, an ionic compound. And the most popular sort of example that illustrates that is something like water, H2O. H2O, when it is together through hydrogen bonding. So there's some bonding that occurs between the positive side of the hydrogen in one water and the more negative side of the oxygen in another water. And that is because water is a polar molecule. So it has a negative side and a positive side. So what happens when we come through and we start heating a bunch of water is essentially the bond that breaks is this bond right here. This is what is known as an intermolecular bond. Force, basically. So that's an intermolecular force. And that is the force that holds one entire water molecule together with another. So as we heat it, we get basically separated water molecules, which then can go into the gas phase as they come apart from each other. And that's because when we heat it, the intermolecular force that holds the two entire water molecules together is much weaker than this one, which is what is known as an intramolecular. Apologize for my pen. It's a little not so great today. So that's an intramolecular force is what I just scribbled there. Intra, I-N-T-R-A, molecular force is the bonds that hold the individual guys together in water, like the O and H bond and the O and H bond. So when we do heat something like water, it breaks that intermolecular force, which separates out the two waters from each other. There's still water in that case, able to go into the gas phase. And that's because it is much weaker than our intramolecular force. Otherwise, if it was the opposite, when we would heat something like water, these bonds would fall apart first and we would get like hydrogen gas and oxygen gas that would generate. And again, we know that does not happen because when we boil something like water to make pasta, we get steam, which is still water, which is still H2O. We don't get hydrogen gas or oxygen gas. Again, you probably want to get to your pasta in that case. So under normal conditions, there are some things that are gases, and these are some of the things that we've talked about before. We have our hydrogen, nitrogen, oxygen, fluorine, and chlorine. These are diatomic molecules, so again, they exist as twos. So H2O2, N2, F2, Cl2. Again, that is naturally how they come. Something like ozone, which is O3, basically three oxygens together, is also a gas. And then obviously on the periodic table, we have our group 8, which is our noble gases. We have our neon, our helium, our argon, krypton, xenon, all the ons there. Those are sometimes referred to as monoatomic. Monoatomic means they basically come as ones, as opposed to our diatomic guys like hydrogen gas, nitrogen gas, and so forth. Here's a little table I made when I was bored, a lot of time on my hands, but have these guys here again in sort of the polka dotted colors there are guys that we normally will find in the gas phase under normal conditions. So it's a good point to talk about sort of a distinction between two words that we commonly will hear. A gas is typically used for a substance that is normally found in the gas phase under normal conditions. So something like CO2, CO, which is carbon monoxide, they're normally gases under normal conditions, and they're found normally like that. Now, that's different than typically something that's known as a vapor. And a vapor is typically something that under normal conditions is a solid or a liquid, but can be converted into a gas form. So again, the most common sort of example of that we all have seen is, again, water. Water we normally find in the liquid phase, but again, like the making of pasta there, when you boil your water, again, it doesn't take a lot of energy or a tremendous amount of energy, and it's kind of easily converted water from liquid phase to the gas phase. That's why we oftentimes will refer to water as the water vapor, not like water gas, for example. We refer to it as the water vapor or steam, so in some cases. But again, we don't usually refer to it as water gas, because it doesn't usually exist as a gas under normal conditions, but it can be converted to a gas, which again is why we usually use the word vapor with it. Any questions on the differences between those things? Okay. So let's talk about pressure. So the majority composition or the major component of air, which is obviously a gas, is actually nitrogen. So nitrogen gas is actually the major component of air, and that's followed by oxygen gas, and then some other gases depending on sort of where you're breathing at the moment as to what's floating in there. But really, actually sometimes surprises people. The major sort of gas that's in air is actually nitrogen, again followed by oxygen. One of the most sort of measured properties of a gas is pressure, and pressure is basically exerted by gases as they're flying around. Again, as they're flying around, they're colliding with the container, and it's those collisions, the number of collisions that occur, that basically affects the pressure of that gas. The higher the number of collisions, the higher the pressure there would be, and vice versa. The smaller or lower the number of collisions as the gas is flying around, the less pressure that would be exerted by that gas. One way that we measure pressure is through a barometer, which looks like that picture I just showed there, but I'll show you in just a second. But a barometer is essentially a glass tube. That's our traditional barometer was a glass tube that was inverted into a pool of mercury, and then as atmospheric pressure basically came down on that mercury, the mercury in the tube basically would rise. And that brought us to some common units that we see in pressure, or for pressure. The first very common sort of unit is atmospheres. So right here. So an atmosphere here is a common unit of pressure. A torr is another unit of pressure, a torr named after the guy who invented the barometer. And this one right here, which is mmHg, that is because in that picture, like we'll see on the next slide, really badly drawn picture here. Let's do it that way. We got the mercury coming up. And when you would look at this tube, there essentially would be like a ruler on it, basically. And one of the units that you can measure is mm, which stands for actually millimeters. And because the MHG really stands, oh, that was cool, it kind of repeated everything. That's millimeters of mercury. So what you want to do is you could use these common units as sort of conversion factors to go from one unit to the next. Again, I would say atmospheres is the most common unit. So one way that we go from it is with this relationship here. 1 atmosphere is 760 millimeters of mercury and 760 torr. So that really is our conversion factors to go from one to the next. So again, if you have atmospheres and you want to go to either millimeters of mercury or torr, I'm gonna have to abandon my pen. It's driving me crazy. Hang on a sec here. All right, we'll go this way. Millimeters of mercury are torr, which is the same. You're going to actually multiply by the 760. So the 760, you're going to multiply by it. And that would get you, again, either millimeters of mercury or torr. And again, they are a one-to-one relationship. So I'll do my best here, but maybe try to turn it up on your side. I'm getting a little bit of some delay. Unfortunately, that's why my pen is kind of going crazy. So I'll do my best. Hopefully, if you're having trouble with the audio, try to kind of turn it up a little bit on your side. Hopefully that will help. And again, I'm starting to notice a little bit of delay here. So with what I'm writing, so I imagine that might be some of the issue as well. So I don't know if it's just the Zoom conferencing at this point. So everything's sort of set the same way as I've been doing it before. So, well, hopefully you'll be able to kind of hear everything, I hope. And again here, the millimeters of mercury and torr are equal to each other. So you essentially could go from those units by just changing the units that are there. You don't have to do any conversion. It's a one-to-one conversion. So that also means if you start with millimeters of mercury or torr, you would want to divide by 760 to get to atmospheres. So these are very common conversions that you do a lot. And that 760 number, again, is sort of an important conversion to allow you to do that. Any questions on that? So for us, atmospheres, torr, and millimeters of mercury are really the common pressure units that we'll come across. Again, there are other ones. There's units like bar. There's units like pascals. These are all units of pressure. But really in chemistry, these are the three sort of common units that you come across: an atmosphere, a millimeter of mercury, and torr. And again, the relationship is basically that 760 number that allows you to go from one to the next. There's a much prettier picture than a barometer. Kind of looks like what I drew. But again, as the atmospheric pressure exerts down here on our mercury pool, the mercury comes here, hence the word mercury rising, right? Is what we see here. Mercury is kind of a weird sort of property. The meniscus with mercury actually is opposite. It goes this way. And you would still do the same thing. You would read from the top of the meniscus in this case. And that's a unusual sort of property that occurs because of mercury and what happens when it's in the tube. So this is actually correct, this kind of curvature in this direction, which again is different than what we normally see with something, say, like water, which curves in that direction. Here are a couple other units of pressure, and again, in our class, you probably won't see too much of pascals, which is what that stands for, or kilopascals, but those are very common units of pressure that we commonly will see. So we're going to talk about a bunch of laws, and the first law we're going to talk about here is what is known as Boyle's law. And when we talk about these laws, what we will see is really we'll be looking at three variables. We'll be looking at pressure, volume, and temperature. So looking at pressure, volume, and temperature, sometimes we may look at all three of those together. We may keep one of them constant and look at only two of them. So when we're dealing with Boyle's law, it deals with pressure and volume, and it keeps constant the temperature. So this is that constant temperature. And basically the relationship that is seen when we have it at constant temperature is basically an inverse relationship. So all this you don't have to worry too much about down here. But basically what this says is when you do something like Boyle's law and you keep the temperature constant, that whenever you take a pressure value and a volume value, it will always equal the same number. So you always get this constant number, and that's really what the K stands for here. That's a constant. And what they found was with Boyle's law was as one goes up, the other goes down. So as the pressure goes up, the volume will go down, and vice versa. As the pressure goes down, the volume will go up. So if you just sort of think about this logically, if you have a bunch of gas molecules in this small little volume here, they pretty much don't have a big area to fly around. So because they're in this very small volume, they are most likely going to collide with the container a lot more often. That's going to increase the amount of collisions that we see, and that is going to cause the pressure to go up. So typically at these small volumes, we see larger pressures. And again, that's because they have really nowhere to fly around. So they keep basically running into each other. Now, the opposite is true if we go to sort of a larger volume. So if we made the volume larger, and we had our gas molecules flying around, these guys now have a little bit more space to fly around in. So as they're flying around, it's going to take longer for them to basically collide with the container. It's going to take longer for them to kind of collide with each other or bounce off of each other. So the number of collisions is going to start to go down. And because the collisions will start to go down, we will see that the pressure will basically start to drop. So just like if we all went into like one small little room and we're all trying to fit in there, pressure would get very high very fast because there's not a lot of room for everybody to move around in, as opposed to if we all crowded into, say, a football field where there's plenty of room, right? There's a lot more opportunity for us to move around before we collide into anything, and the pressure would be less. So the way that we sort of manifest Boyle's law is with this equation here, and this right here in the box, and all these gas laws that we see that are in boxes, you do need to know. And this is basically Boyle's law. This is P1 times V1 equals P2 times V2. This is like a before and after type of deal. And in terms of the units that we have here, in terms of pressure, they could be any units you want. And also the volume here can be any unit that you want as well. So the volume and the pressure here can be any unit that you want to put in there. The key, though, is it does need to be the same unit of pressure or volume on each side, which means on the left-hand side, if you have atmospheres, and on the right-hand side, you have torr or millimeters of mercury, you need to convert one of those. So you need to convert one of those to the same unit. You can either convert them both to atmospheres, you can convert them both to torr. The same thing with the volume. It could be milliliters on both sides, it could be liters on both sides, but it does have to be the same unit. And what we see here from this curve, which is a Boyle's law curve, we see what we were talking about here. We see very high pressure at low volume, while over here we see that the pressure has decreased as the volume has increased. Again, giving everybody a little bit more room to fly around. So why don't you give this a go, and then we'll talk about it here. A balloon is inflated to 0.55 liters at 1 atmosphere, rises to 6.5 kilometers, where the pressure is 0.4. Assuming that the temperature remains constant, what is the final volume of the balloon? So why don't you take a moment and give that a go, and then we'll talk about it. Okay, so here, and with lots of gas problems, one of the best things that you could do is, although we only have one gas law at this point, we will have a lot more gas laws as we continue through. Um, One thing that you can do is kind of pull the information out from the problem. And a lot of times when you pull the information out from the problem, you could kind of label it, and it will really point you in the right sort of direction in terms of what gas law you should use. So here we have 0.55 liters, which is a volume, and it goes to 1 atmosphere, which is a pressure. So we have a pressure and we have a volume given to us. It goes to 6.5 kilometers, which is really useless information in this problem. And it goes to a pressure of 0.4 atmospheres. And so we have another pressure, and we're looking for a volume here. So you can see by labeling these things, if you weren't sure, it really should kind of point you to Boyle's law in terms of the answer that, or the formula that you should use. So in this case, we are solving for B2, which is here. So we essentially want to divide P2 to the other side, right? And by the way, when you move something across the equal sign, it ends up in the opposite location. So P2 is on top. It ends up basically on the bottom when you do that, and you cancel each other out. So doing that, we'll rearrange it like here. We want to make sure that we take V1 times P1 divided by P2. We want to put all the numbers in correctly in the right locations. Our atmospheres here will cancel, and that's going to leave us liters as our unit that's left over, and we will end up with 1.4 liters. Any questions on that? Another very important thing in terms of making sure that your answers make sense is, again, remembering sort of the relationships that we talked here with Boyle's law. Pressure goes up, volume goes down, and as the pressure goes down, the volume will go up. So here we can see that our pressure went down, which means we should expect our volume to go up. And it did. It started at 0.55 liters. It ended at 1.4 liters. So sort of what we expected to happen actually did happen in this case. Any questions on that? So the next sort of relationships that we're going to look at are ones that deal with volume and temperature, and volume and temperature, keeping constant pressure, while we're looking also, we'll be looking at pressure and temperature, keeping constant volume in this case. This is Guy Lusix, should be an A, I think. So let's take a look at this relationship here first. When we look at this relationship, what we will see is if we have a container where we keep it at constant pressure, constant volume. So if we have constant volume here, our gas molecules here flying around. If we increase the temperature, that means that these gas molecules will then gain more energy, which means they should be flying around a lot faster. And because they're flying around faster, there's going to increase the collisions that we see. And because we're increasing the collisions, that should mean that the pressure should also go up. So the relationship that we see here at constant volume is if the temperature increases, so should the pressure. Again, because the volume is fixed, it's not going to go anywhere. It's staying exactly where it's at. So all we're going to get are gas molecules flying around a lot faster, causing more collisions and more pressure. Opposite is true if we lower the temperature. So if we drop the temperature, that means that these gas molecules here will start to fly around a lot slower, which means they're, even though they're in a very fixed volume, they're going to be flying around slower, which means the rate of collisions are actually going to decrease the collisions. And because the temperature will decrease, what we would see in that case is the pressure would also decrease in that situation. And that's what's really known as Guy Lusix's law, which is this guy over here. So Guy Lusix's law. And that is basically it, when we have a constant volume, if you raise the temperature of the gas, the pressure should increase, and vice versa. If you decrease the temperature of the gas, the pressure should start to come down. Now, that's different than really what's known as Charles' law, which is this guy here. So Charles' law. Really, Charles' law deals with volume and temperature and constant pressure. So we have our gas molecules here at temperature 1. And we move our gas molecules over here to temperature 2, which is a higher temperature. What's going to happen is the volume is actually going to increase to accommodate that higher temperature. And that is the way it's able to maintain constant pressure in this situation. So this is the way it's able to maintain that constant pressure. Is by adjusting the volume as the temperature goes up, for example. And what we know is if the volume doesn't adjust and we raise the temperature, we would see what Guy Lusick saw, that the pressure should increase. But the way it's able to maintain constant pressure, it's able to maintain constant pressure by adjusting the volume in Charles' law. So by adjusting the volume in Charles' law, it's able to maintain that constant pressure. And vice versa, if we were to take our second temperature and it was actually lower than our first, what's going to happen is if we lower the temperature, the gas molecules will no longer be flying around as fast. They're going to be flying around slower. And that means in order to keep the pressure constant, the volume would have to come down. So as the volume starts to decrease, that means that's going to keep the rate of collisions up and constant, and that will keep the temperature, that'll keep the pressure constant as well. So with Charles' law, what we see is kind of the same relationship. The volume will increase as the temperature increases. Again, because as we increase the temperature, more collisions. So to keep constant pressure, the volume also increases with it, and vice versa. As the volume goes down, the temperature will go down, or however you want to say that. As the temperature goes down, so will the volume as well. And that's, again, for this situation here, they want to drop the volume down to keep those collisions rate up and keep it from, kind of lowering the pressure and stuff like that. So those are the two sort of relationships that we see here. Guy Lusick's law over here, as the pressure goes down, temperature will go down with it. As the pressure goes up, the temperature will go up, again, because we're at constant volume in this situation. And Charles' law, which is as the volume goes up, the temperature goes up, volume goes down, temperature goes down, and we will see the volume adjust here to keep it at constant pressure. So those are the two relationships. Okay. So for a, let me come back to that in just a second before we talk about the actual laws. But what Charles basically saw was, he saw that if you plot a graph of volume on the y and temperature there on the x-axis for any gas you like, and if you take that line and you extend it all the way back to the temperature line, every gas, no matter what gas it is, will basically hit the exact same spot. It will hit minus 273.15 degrees Celsius. And you should recognize that number. That is the number that we typically will use to convert to Kelvin. And that's a very important significance here for gas laws. It essentially means when we see gas laws and we see temperature, the unit it has to always be in is Kelvin. And this is sometimes called absolute zero, and that's because it's minus 273.15 degrees Celsius, which means if I wanted to convert it into Kelvin, I would add 273.15. And that would give me 0 Kelvin, which was originally called absolute zero. And this was usually called the absolute temperature scale, later named after Kelvin as well. So pretty safe bet if you're doing any type of gas law type calculation, you will need to use Kelvin in his calculation. So again, a reminder to convert to Kelvin from Celsius. That is our guy down here that we've learned way back when. Again, just like usual, you don't have to use the 0.15 if you don't want to. You could just use 273. But pretty much Kelvin recognizes the behavior of these gases, and that is essentially why we use Kelvin in every single gas law that we see. So looking at those two really laws that we talked about, and I'm going to really break this up the right way here. Really, this guy down here is usually what people think about when they think about Charles' law. Guy-Lussac's law over here is usually this gas law, which is P1 over T1 equals P2 over T2. So this is usually what is referred to as Guy-Lussac's law. This is that constant volume. Over here, the bottom is basically Charles' law. This is usually what we talk about was Charles' law. And this is just like Charles' law. This would be at constant pressure. So this guy up here is the relationship that we talked about. Pressure goes up, temperature goes up, and vice versa. Pressure goes down, temperature goes down. And the guy down here is the relationship. Volume goes up, temperature goes up, and volume goes down. Temperature will go down as well. Now, in terms of the pressure that we have up here, pressure could be any unit you like. Again, as long as they are the same on both sides. So you can use atmospheres on both sides. You could use millimeters of mercury on both sides. You can use torr on both sides. The key here is the bottom. This one, in every gas law, you got to use Kelvin. So you got to have the temperature in Kelvin. Same thing down here for Charles' law. Also needs to be in Kelvin. The volume doesn't matter in Charles' law. You can use it in milliliters. You could use it in liters. You can use any unit you want, but it does have to be in Kelvin. Now, when we look at these two gas laws, we want to make sure that we do rearrange them. You want to rearrange them correctly, and the same rule applies as we go across the equal sign. Things do end up in opposite locations. Again, so for example, if I was moving the volume, the V2 to the other side, again, it would end up on the bottom, and vice versa. If you're moving the T2 to the other side, it would get to the bottom as well. So these, you do need to know these sort of gas laws as well, and obviously how to solve for any of these guys, any of those sort of variables there. Any questions on that? All right, so if you do have questions, feel free to type it. If not, why don't you work on this one here? We'll go over it in a minute or two. We got 452 milliliters of a gas. It's going from 22 degrees to 187 degrees at constant pressure. What is the final volume? See what you come up with, then we'll talk about it. Yeah, so that is correct, Eric. The temperature does need to be in Kelvin. That's really the only restriction. So for Charles' law, the volume can be any unit you want, milliliters, liters. For Guy-Lussac's law, which is the P1 over T1, the pressure can be any unit you want, atmospheres, millimeters of mercury, and that type of thing. But really, pretty much for every gas law, always got to be in Kelvin. And that also includes questions where you might come across something where it gives you the temperature in Celsius and wants you to give the answer in Celsius. And even though they give it to you in Celsius, they want you to give the answer in Celsius. You still have to convert it from Celsius to Kelvin, then put it into the gas law, and then convert it from Kelvin back to Celsius. So sometimes people see those type of questions where they're like, hey, they gave it to me in Celsius. They want the answer in Celsius. I'm just going to leave it. And you can't do that. You do have to convert it to Kelvin, go into the gas law, and then actually convert out of it as well. So that's one major restriction in terms of gas laws is the temperature one. Always got to be that Kelvin. You're welcome. All right, so why don't we look at this one here? So remember that, again, now that we got a few more gas laws to look at, if we take the information and pull it out, we see we have a volume that is 452 milliliters. We have a temperature that is 22 degrees Celsius. We have another temperature that is 187 degrees Celsius, and we're looking for a volume. So again, now that you have sort of some choices for the gas laws, if you just kind of pull the information out of the problem and sort of label it, Charles' law really should kind of stick out to you as sort of the right one to use here. Again, we do want to use Charles' law. As was just asked the question, when we use Charles' law, which is our V1 over T1 equals V2 over T2, again, it is that temperature that we need to convert. So we would want to convert the two temperatures by adding 273 to each of them to convert them to our Kelvin. So if we do that, what we see is we end up with 295 Kelvin for our 22 and 460 Kelvin for our T2. And again, in this case, we are looking for V2. So you're basically going to multiply the T2 to the other side, or again, it ends up in the opposite location. So if we rearrange this, V2 would equal V1 times T2 divided by T1. So again, if you just kind of move it to the opposite location, that's a quick way to rearrange the equation. We obviously, again, want to make sure that we put everybody in the correct locations. And when we do, we will see that the temperatures will cancel. So the kelvins will cancel out. That will leave us milliliters, which is good because we are looking for a volume. So we're going to take 452 times 460 divided by 295, and we will end up with 705 milliliters as our final volume. Any questions in this case? Again, understanding the relationship of Charles' law. So if you remember when we talked about Charles' law, as the volume goes up, so will the temperature. And as the volume goes down, so will the temperature. So when we look at this problem, what we see is our temperature went up. So we would expect as we go this way that our volume increases as well. So here we went from 452 to 705. So we did see that increase in volume like we would expect to happen. So again, that's just a good way to check yourself just in case you maybe put the wrong number of or rearrange the equation incorrectly. We are We're ending at 705 because really of the 452 is where we ended with the 3 sig figs. Technically, when we added this together, we got 460, which the way I wrote it here would technically be 2 sig figs. But probably we would want to look more at this number. Again, as we talked about with temperature conversions, they don't necessarily follow significant figures all perfectly strong and strongly there. So probably would go back to this number here and end up with 3. If you did 2, I could understand why you would do it based off of this part of the calculation. But that's why we end up with 705. Other questions? So another law to add to our ever-growing list is our good friend, is our good friend Avogadro. He had a number, but he wanted a gas law as well, so why not? So Avogadro's gas law basically is V1 over N1 equals V2 over N2. Yeah, so before we get to here, we'll go back real quick. This right here is basically what's considered Charles' law. The one with the P1 over T1, like we saw before, equals P2 over T2, is usually was referred to as Guy-Lussac's law. But usually this is the one, this is Charles' law here, is the one that most people think of, and that actually is Charles' law. This is more Guy-Lussac's law over here. They're very similar in terms of their relationship because they both dealt with temperature sort of relationship. So a lot of times they're kind of comboed together. But most of the time, this is definitely Charles' law here. Again, Guy-Lussac's law on that side. So Avogadro's law is the relationship between volume and N, and that's V1 over N1 equals V2 over N2. And V is volume, so same rule applies here. It can be any unit you like in terms of the volume. N is actually moles. So N is moles. And that's what the N stands for. And when we look at Avogadro's relationship, this occurs typically at a specific time. This occurs when we have constant temperature and pressure. So when you hold something at constant temperature and pressure, that is basically where we get the relationship known as Avogadro's law. V1 over N1 equals V2 over N2. Basically what it says is the number of moles of gases basically will be the same as the volume. So as the moles of gas increase, so does the volume of the gas, and vice versa, the volume of the gas will decrease as the moles will decrease. And that's what we'll see here in this little picture. N equals 1, we have this. As N goes to 2, we see that the volume will double. N goes to 3, the volume will triple as well. And this also could come into play when we talk about stoichiometry involving gases and sort of that mole-to-mole relationship. So let's just say we had 2A, which is a gas, plus 3B, which is a gas, goes to 4AB. We'll assume it's balanced and all that good stuff. That goes to a gas. So when we do stoichiometry, right, we can, for example, say there are 2 moles of A that reacts with 3 moles of B. And we could do all of our conversion factors and stoichiometry sort of conversion factors from that equation. If this was at constant temperature and pressure, we could also do like a stoichiometry relationship here, but instead of using these coefficients as moles like we did before, we could use them as liters. We could say there are 2 liters of A reacts with 3 liters of B. So it works kind of the same way as stoichiometry. So if you're doing a stoichiometry problem that involves gases, it's kept at constant temperature and pressure. Instead of doing a mole to mole relationship, you actually can do a volume to volume relationship using Avogadro's law, basically, as a way of doing that. So if I said I had 5 liters of A, and I wanted to know how many liters of B I would get, you could do an exact same sort of stoichiometry problem, but using liters, where you take the 5 liters of A and use basically that liter to liter relationship as a conversion factor. So 2 liters of A from the equation gives me 3 liters of B. The liters of A will cancel. That will give me the liters of B, which in this case would be something like 7.5 liters. So this sometimes will provide you a shortcut instead of having to use something like the ideal gas law, which we'll talk about in just a second, or do a mole to mole relationship. You could actually do a liter to liter relationship using basically stoichiometry, and those as volume. Again, can only occur when you got gases in a reaction. And the other thing, Avogadro's law, in that sort of relationship has to be at constant temperature and pressure in order to do that. Any questions on that there? Obviously, as well, you can just plug and chug into this equation if you have 3 of the 4 and solve for whatever's missing. You could also just go right into that equation. This is sort of a second aspect of Avogadro's relationship that allows you to sort of do like a stoichiometry problem using liters to liters instead of like a mole to mole relationship. Any questions on that? So that does bring us to, the granddaddy of them all here. If we combine pretty much everybody there, Charles' law, Boyle's law, Avogadro's law, yeah, so in terms of Avogadro's relationship, as we see in this picture here, let me just go back to it. As we see in this picture here is they basically will change kind of equally. So here we have 1 volume, for example, and 1 mole. And if we increase the mole, which is essentially doubling the amount of moles of gases we have, we see that the volume also doubles. And same thing here, if we go from this first one to the last one here, and went from 1 to 3, which is like tripling the number of moles. And what we see for the volume is it also triples. So the volume and moles in terms of Avogadro's relationship basically will change equally in that sense. So if you double the moles, you'll get double the volume. If you kind of triple the moles, you get triple the volume. And vice versa, if you go the other way, obviously the same would happen. If you decrease the moles, by a factor of 3, the volume will go down by a factor of 3 as well. So that's why they kind of change almost like equal to each other. And that's what allows you to kind of do a very similar relationship like we use with moles using volume. Any other questions on that? Okay. So this is, the big equation here, which is the ideal gas law, which basically relates pressure, volume, and temperature to an ideal gas. So what makes something an ideal gas, which is essentially all the gases that we deal with in this class, we'll talk about real gases just a little bit towards the end of this chapter, but essentially we deal with pretty much all ideal gases. You go in, when you take 1A, you'll deal with real gases. But what makes something an ideal gas is essentially we can treat them as almost they were by themselves. Even if there were other gas molecules there, we could kind of treat them as individual and sort of by themselves. And combining all those previous gas laws, we get the ideal gas law. And the ideal gas law is PV equals nRT. And the first thing that you should notice from this gas law is it is not a like before and after situation like all the other gas laws that we had. All the other ones we had, say, 2 pressures, we had 2 volumes, 2 temperatures, whatever it may be. Here it's just a one set of conditions. You'll have 1 pressure, 1 volume, 1 temperature, and 1 mole, and so forth. So the other important thing about this equation is out of all the gas laws, this is the one that is the most restrictive in terms of the units. So when you use the ideal gas law, you have to use everybody in their correct units for things to work out correctly. So what that means is when you use the ideal gas law, the pressure has to be in units of atmospheres. So if you have something that's in millimeters of mercury, you have something that is in torr, you need to convert it into atmospheres before you go into this formula. Volume as well is also restricted to having to be liters. So again, if you have some other unit of volume like milliliters, you need to convert it to liters. Again, commonly you will get milliliters. So a reminder that there are 1,000 milliliters in 1 liter. So that's a very common conversion that you have to use. Temperature, like everything else that's a gas law, also has to be in Kelvin, which is pretty much like everybody else. And N, which is moles, should be in moles unless you did something wrong. But it should be in moles. And a very common thing that will happen is you will be given information, not in moles, but you'll be given information in grams. So a reminder that to go from grams to moles, that is our molar mass, right? That we use as a conversion factor. So that is our molar mass from the periodic table that we use for our conversion factor. So that is something that's sort of used a lot with the ideal gas law because you're given things in grams. Again, other common conversions you'll need to use when using this one, the milliliters to liters, 1,000 milliliters to the liters, common. And then obviously our 760 number, our torr, our millimeters of mercury equals an atmosphere. So these are sort of 3 common conversions that you may not always have to use in this when you're using ideal gas law, but a lot of times you'll have to use these guys to convert everybody to the right units. And the reason really that everybody has to be in those units is because of R. R is the gas constant, which means it is a constant value. It also means that you always have this number available to you, even if they don't specifically say in the problem, the R value is this. It is just a number that you will always have available to you. And the number is 0.08206. And some people will round this number to 0.0821. So that's a very common rounding of that number that people use. But more importantly, this gas constant, which is always that number, has 4 different units. It has liters times atmosphere on top, divided by Kelvin times mole. So the gas constant has all of those units, and those are all the units that everybody else has to be in order for things to cancel. So the good news is this number is usually provided for you somewhere on a conversion sheet or something like that, which means the units are provided for you. So if you ever forget what units things need to be in, you could look at R and it will tell you the units that everybody has to be in. In terms of R, I don't really have a preference. Personally speaking, for the value of R, I will use 0.08206 because that's the number they beat in my head and I cannot get it out. I try, but I can't get it out. But it's very common. A lot of people will round it to the 0.0821. In terms of the answer and stuff like that, it probably won't make a tremendous difference in most cases. So it's your preference. If you want to use the 0.08206, that's perfectly fine. If you want to use the 0.0821, again, most of the time I probably will use the 206 part of it. But again, they're both perfectly fine. You can use either one you like. Same thing here. If you need to solve for any of these guys here, you could just divide to the other side, whichever side you need to divide them to. Any questions on the ideal gas law there? Okay. So another couple of important relationships, and this is how we actually get to that number, and we'll see that in just a second. But we'll start here with STP. STP stands for standard temperature and pressure. So in a problem, they will sometimes say, what is the volume at STP? Or this is at STP. So when they give you STP, they're actually giving you values for each of those things. When they say STP, that means the temperature is 273 Kelvin. And the pressure is essentially 1 atmosphere. So if they in a problem say, hey, we're at STP, they are actually giving you those two values. It's understood that you know that the pressure is 1 atmosphere and the temperature is 273. Now, there is a special relationship when you are at STP, and this is at STP up here. So if you are at STP, what this says is you could take 1 mole of any gas and it should have a volume of 22.414 liters. And this also is a conversion factor that will sometimes allow you not to have to use the ideal gas law for solving a problem. You can use the ideal gas law in any situation. It could be an STP situation, a non-STP situation. But this sort of conversion factor here is again only at STP. So if the temperature is not 273 and if the pressure also is not 1 atmosphere, you cannot use this conversion. You have to use the ideal gas law. But if it is at STP, you will have a choice in how you could solve a problem. You could either solve it using the ideal gas law or you could use that relationship. Any questions on that? So again, that 1 mole equals 22.414 liters is specific for STP conditions, which again means that the temperature is 273 Kelvin and the pressure is 1 atmosphere. If we do take the ideal gas law and solve for R and put in all of our values at STP, which is our volume there, 22.414, or 1 mole, 273 1 atmosphere, this is actually how you do get to the value of R. And again, most people will round to here, R to here, which is that 0.0821 number. Any questions on that there? Why don't you give it a go? And again, if you do have questions, feel free to type them in and I'll answer them. If not, we'll talk about this in a minute or so. So we want to calculate the pressure here exerted by 1.82 moles of SF6 gas in a steel vessel of volume of 5.43 liters at 69.5 degrees Celsius. All right. So again, you can pull out the information and it will kind of lead you to the right sort of answer, hopefully. We're looking for a pressure here. We do have 1.82 moles, so that's N is 1.82. We do have a volume given to us, which is 5.43 liters. And we do have a temperature that's given to us, which is 69.5 degrees Celsius. So just looking at this, we have a P, we have a V, we have an N, we have a T. We only have one of all those things. And again, you always have R available to you. So that should hopefully put you towards the ideal gas law as probably the proper gas law here to use. And we want to look at everything, right? Because remember, our PV equals nRT. Pressure needs to be in atmospheres, but we're looking for that, so we're not going to worry about that. Our volume needs to be in liters, which it is, so that's good. Our moles should be in moles, which it is. Our gas constant is constant, so that's okay. But just like normal, our temperature here does need to be converted to Kelvin, so we would want to make sure that we do that before we go into it. If we solve for P, we're going to divide V to the other side, and that will give us P is equal to nRT divided by V. And if we put our numbers in, again here, converting our temperature to Kelvin, which gives you something like 342.5 Kelvin, I believe in this case. Here you see I use actually in this case the 0.0821 number. In terms of units, our liters will cancel, our Kelvin will cancel, our moles will cancel. So the only unit left is atmospheres, which is good because we're solving for a pressure. And if we put all that in, we end up with somewhere 9.42 atmospheres as our pressure. Any question on that conversion? Again, in most cases, you do have to, a lot of times, like we did here, convert to Kelvin. I would say a lot of times, yes, this might be in milliliters, so you'll have to convert to liters. And again, a lot of times, this may be in grams that you have to convert. Any questions on any part of that steps there? I thought you were giving me a quiz. Okay. Yeah, what's your question? Why did I write ATM in the numerator? Yeah, so this part of it here, I think you're talking about right here, right? And that part of it is the R value. And remember that R is basically 0.0821 or 206. But this value here actually has 4 different units. So it's liters times atmosphere divided by Kelvin times mole. So unlike a lot of things that have usually just one unit associated with it, the gas constant actually has all 4 of those units associated with it. So when we put it into R, that is how the atmosphere gets up on top. And that is the only unit that's left over. Like I boxed over here, that's the only unit that's left over after all the other units cancel out. So that's why R has all 4 of the units involved in the ideal gas law, because pretty much 3 of the 4 units will cancel out when you solve for anything, and that will leave you the correct unit that you're looking for in that case. Yeah, you should when you show your work, obviously you should include all the units, and that includes all the units for R as well. That way you could hopefully clearly see what's canceling out. I'll be honest with you, sometimes people maybe don't have the best understanding sometimes of units and stuff like that. So sometimes we'll get something like the pressure is like, 32 milliliters, where milliliters is the volume and stuff like that. So you want to make sure that obviously you put in all the units there, and that way you can see them cancel out like I did up there in the middle. And you could also hopefully see what unit is left over. Other questions on that? Okay. Now, there is another gas law because, we don't perhaps have enough yet. So we'll keep going. I'll talk about all this stuff I'm scrolling through. Perfect. All right. So there is a gas law that pretty much deals with all three of those variables together. That's pressure, volume, and temperature. And this is what is sometimes referred to as the combined gas law. So the combined gas law, when you do all of those kind of steps ahead up here, taking the ideal gas law, solving for R, because this is a constant, you can set them together. And usually in most cases, the moles of the gas doesn't change unless you open the lid, right? So if you keep the lid shut there on the gas, usually the moles can't escape because they're trapped inside the container. And that gives us this relationship here, P1, V1 over T1 equals P2, V2 over T2. This again is what is referred to as the combined gas law. And it deals with both pressure, volume, and temperature perhaps changing altogether. A couple of things in terms of units. Pressure and volume here can be any unit you like. And just like all the other gas laws, our temperatures do need to be in Kelvin. That's both temperatures there. T1 and T2 needs to be in Kelvin. So pressures again here can be atmospheres, it could be millimeters mercury, they could be torr. Volume could also be milliliters, liters. Again, as long as they're the same on both sides, everything should cancel out sort of correctly. This, I think, would be the one that gives people sort of the hardest time in rearranging it. So if that's sort of a problem for you, you want to take a moment to make sure that you know how to properly rearrange all these type of things. Any questions up to there? Okay, so I think this is what we're going to do is we're going to stop officially lecturing right now. We're going to take about a 10, 15-minute break, and then we're going to go to the lab. And I'm going to actually continue to lecture this chapter in lab just to kind of keep us on track and keep us on pace. You might have noticed I moved the pre-lab that was scheduled for today to Monday. And I think hopefully after lab, we should get through most of this chapter, which will then allow you to sort of understand the experiments that are coming up. So we have 2 gas law experiments that are coming up. Unfortunately, I don't want to let you kind of do the first one yet because we haven't gotten far enough in lecture for you to be able to probably answer all the questions and stuff like that. So what I'm going to do then is we actually are going to be lecturing in lab coming up. So we'll start that, like I said, about 10, 15 minutes after we finish here. And we will continue to lecture this chapter. Yeah, so this is sort of my goal and my thought is, yeah, so we are, yeah, the lecture will be recorded and will be posted. Everything will be up online like normal. So that lab lecture will be up. So you could listen to it if you need to, but you will, I will continue lecturing during lab this way. And then after I'm done, pretty much both gas labs will probably be due next week on maybe Monday or Tuesday, but it should at least allow you to do those 2. So the one that's 17 was moved to Monday, the pre-lab, and officially, we'll either start it officially after lab today, and it won't be due until probably Tuesday. And that one and the one on Monday will also be due on Tuesday. So just so we're clear, the one that's technically going to be scheduled for not for Monday, we're still going to do on Monday as well. So you'll have 2 gas experiments. They're kind of similar. And then they both will be due and uploaded probably Tuesday of next week, if that sort of makes sense. Yeah. Okay, so we'll take like a 10, 15-minute break. So maybe like 12:05-ish. we'll hook back up in the lab meeting. That way everything will be recorded sort of separately, kind of pick up where you need to. And we'll continue lecturing from right here where we left off. So I'll see everybody in about 15 minutes or so, okay? So I'm going to stop this meeting and we'll head to the next one.